Hi, welcome back to Astronomy 112. We had to cancel class this week one day because of technical problems. So this is the lecture that was originally scheduled to be held on Thursday. And we're still talking about chapter 16 and the Milky Way galaxy. Remember, so far in the last lecture we had, we learned that the Milky Way, where we live, is a disc-shaped galaxy full of stars, star clusters, interstellar gas and dust, dark matter. There are two general kinds of star clusters, globular ones that a whole lot of stars pushed together into a spherical shape, and open clusters that are more spread out and not as big. And then there's also stellar associations where the stars are not gravitationally bound to each other, but are loosely in the same part of the sky. We divide the stars into two different populations. So what we call population 2 are the older ones, and they are typically not in the plane of the galaxy. And population 1 are the younger stars, like the sun, that are generally in the plane of the galaxy. There's also a lot of interstellar dust that blocks light from stars from behind it and threatens the light. And there's lots of gas clouds, and some of these can be heated and ionized by bright stars, and we call them H2 regions or emission nebulae. But what about cold gas? There's also a lot of cold gas in the Milky Way, and it's not hot enough to be ionized and emitting light in that way. But it turns out that electrons have an interesting property that is the equivalent of them spinning. Imagine these little electrons rotating this little Earth orbiting the proton nucleus, and every now and then the direction that it's spinning can flip from up to down. And when it does that, it emits energy, emits in the form of electromagnetic light at 21 centimeters. So radio waves are emitted by hydrogen when this happens. So this can happen at low temperatures. So this allows us to detect where hydrogen is throughout the universe with radio wave light. And when this is done, that's what these orange symbols are. We saw this graph last time showing the blue symbols are optical measurements of where emissions H2 regions are. And when we do the same with radio of where cold hydrogen clouds are, we see that like the H2 region, they are lined up in the spiral structure. So this tells us that the Milky Way is a spiral galaxy, just like the spiral galaxies we can see outside the Milky Way, where we can actually see the spiral. This is the way we've inferred that the Milky Way is a spiral galaxy. And the sun is sitting right about here relative to these gas clouds. And then, of course, radio waves also allow us to measure other things because there's a lot of different molecules are present in space. And when they vibrate, they emit light, again, often in radio waves. So radio telescopes can detect all kinds of molecules. So these very, very cold clouds are very different from stars in that they're cold enough that the atoms can come together to form molecules. And we call these molecular clouds. And these are the list of a large number of molecules that have been discovered. There's a lot more complicated organic molecules that have been discovered than just these lists. This is the most common molecules in the galaxy. And then astronomers are constantly finding new ones. So how do stars move in the galaxy and gas? And we know they're in orbit around the center of the galaxy, just as the Earth is in orbit around the center of the solar system, the sun. Each gas cloud, each star has its own orbit going around the center of the galaxy. But we see these spiral arms. So the first thought is, these spiral arms, rigid things, are the stars in a spiral arm all moving together as one big block? And the answer is no, we know they're not, because we know that stars are moving faster at the center of the galaxy than the outer galaxy. This is an animation from Wikipedia showing that if you treated them as rigid blocks, the spiral arms would grow together pretty rapidly after just a few orbits. And you would not preserve this spiral form. In fact, you just kind of have these circular things that all form end up forming a block. So there are two theories commonly used together to explain the spiral structure of galaxies and how they look. The first one was developed in the 1960s. It's called the density wave model. And the basic idea there is that as the stars and gas are traveling in the disk around the center, they will bunch up as they enter a spiral arm, and then will sprout out again as they leave. The textbook has a nice analogy talking about cars bunching up on the highway, where if you have one car going slow in the right lane of the highway, other cars will slow down and bunch up behind it. But then some of them will leave to pass that car and other ones will come. So you have this bunch of cars kind of moving at one speed down the highway, but it's not the same cars. It's a clump a clump that is made up of individual cars that are changing all the time. Similarly, the spiral arm is made of stars and gas clouds that are changing over time and moving in and out. And interestingly, you can see that as, say, one of these little interstellar clouds enters one of these spiral arms, the increased gravity of the spiral arm, because things are bunched up there, can compress the cloud to make it start forming new stars, trigger this collapse to make new stars. And of course, the first stars that are made are the most massive and brightest, the O stars and B stars. And they illuminate the gas and dust in the arm, which makes the spiral arms much brighter, partly why we see the spiral arms so clearly in external galaxies. And then they will actually die before leaving the arm region, and again, making the spiral arms more consistent. This model works pretty well. It explains the longevity of the spiral arms and no, it doesn't. Sorry. The theory explains the aging of O and B stars, which you can see across the arm, but it actually doesn't work perfectly for explaining the longevity of spiral arms. So it's not a perfect theory, but it's the main one people are considering today. Another model that's important is called the self-propagating star formation model. And it basically takes into account that this triggering of star formation is kind of random. And that should mean that the spiral arms are not perfectly straight, but should be kind of ragged looking. A lot of galaxies are like that. And the idea is that at some point you have star formation beginning in the galaxy, and you make these new stars. And those stars keep the gas around them, and the larger ones explode. And this sets off star formation in another gas cloud nearby. So you have this kind of triggered wave of star formation. But these things are moving around the galaxy at different speeds. It's slower as you move away from the center, and that spreads these stars out into a spiral arm. So it's not the density wave, it's just formation of stars triggering each other and then getting stretched out due to differential rotation. Almost certainly, both of these models play a role in the formation of spiral galaxies like the Milky Way. But it is very, very much an active area of research for astrophysicists. So we talked about the size of the Milky Way when we began this chapter, but I didn't really talk about how we measured the size of the Milky Way. And there are two general ways we measure the size of our galaxy. First uses something called masers from red giants, and the other uses globular clusters, which we talked about in the last class. So what is a maser? A maser is like a laser. Laser light show at a concert. We're very familiar with lasers that work in optical wavelengths. The same physics effect happens naturally in some red giant stars due to excited molecules, and they generate out beams of light like lasers, only at the microwave frequency. You detect it with radio telescopes. But the physics is analogous to lasers, and it's again associated with certain types of red giant stars. So how does this work? Well, the point is that these red giant sources turn out to be quite common in the inner part of the galaxy, where you have this bulge around the center of the galaxy. And you imagine these stars are moving in random direction. And the idea is to measure their speed and to measure the speed of these red giants, either by using Doppler shifts if they're moving toward us away for us, or by looking at how their position changes on the sky over time. And what we can then do is assume in a given volume the stars are all moving at the same speed. And if we think these stars, we've measured an apparent speed, we think they're all measuring the same speed, we can calculate the distance to these stars, and we can calculate the geometric center of these stars. So this one's moving over here, this one's moving over here. Basically find the average because we think they're all orbiting the center of the galaxy. And when we do that, we get that the sun is at a distance of about 7,000 parsecs, 7 kiloparsecs. So that's one method. Another method uses globular clusters. Now remember, globular clusters are these sphere-shaped, sphere-ish because they have so many stars, they also include a lot of giant stars and variable stars. And remember, when we talked about the Hertzsprung-Russell diagram, we talked about two types of yellow giant stars that are pulsating, the RR Lyrae and the Cepheid variables. And the cool thing about both of them is that they can be standard candles, because exactly how bright they are depends on how fast they're pulsating. So if you measure the apparent brightness, you can calculate their true luminosity from their period and calculate their distance quite precisely. And there's lots of these globular clusters around the center of the galaxy. And when you do this, measure lots of these, again, you can find the geometric center of these because everything's orbiting the center of the galaxy. When you do that, you discover that the sun is at 8.5 kiloparsecs from the center. And that's more accurate than the Maser method, and this is the expected difference distance of the sun to the center of the galaxy. And of course, once you find the distance to the center, you can also measure the distance to objects, find the most distant object you can in the opposite direction of the center, and add that distance. And when you do that, we can tell that the diameter of the Milky Way is at least 40,000 parsecs. Now, you're dropping off very gradually out here. It's very hard to define an exact edge when you get to the edge of the galaxy. This is, of course, not the Milky Way, but it's another spiral galaxy seen edge on. So this number, it's hard to be very, very precise, but that's the order of size of the Milky Way galaxy. So that's the size. How do we determine this mass? And astronomers have used two different ways to infer the total mass of the Milky Way, using Kepler's laws and rotation curves. So remember, Newton's modification of Kepler's law can be written as the mass of the two bodies orbiting each other. Again, it's like just Kepler's third law is related to the radius cubed over the period squared. And in the case of, if we're going to consider the sun versus the rest of the galaxy, we're basically considering all of the mass interior to us to be the equivalent of a single mass at the center of the galaxy. This is perfectly consistent with the laws of physics, with Newton's laws, to treat the galaxy this way. So we imagine the sun is orbiting the rest of the galaxy inside it. And little m in this case is very small, so we omit it. So we basically say capital M equals r cubed over p squared. We actually know r from using the Masers, I said rotation first, I meant globular clusters, and we can measure the velocity of the solar system relative to the galactic center to get, and then you figure out how long it takes to go around the galaxy. And when you do this, and this calculation's in the textbook, we put things into the right units because Kepler's third law is in terms of astronomical units in years. We're at 1.5 billion astronomical units from the center of the galaxy. We orbit the center of the galaxy in 220 million years. And you plug all that in together, and you end up with the mass of the galaxy is about 10 to the 11th solar mass, 100 billion solar mass. That's very, very big. You can also measure it using what we call rotation curves. And rotation curves are, basic idea is that if you can measure how fast stars are moving, different stars are moving at different distances from the center of the galaxy, and make a graph of the rotation speed versus the center, and then use Newton's laws, you can calculate how much mass is interior to each one of these stars from the speed that they're going. And this is this can be used for the entire mass of the galaxy, not just the galaxy interior to its orbit. And of course, to do this, you actually need to be able to measure the speeds of the stars. And again, we can do this for individual stars using Doppler shifts or seeing how their position on the sky changes over time. But you need a reference because we are moving as well. So we're trying to get their velocities relative to the center of the galaxy. And so we have to subtract our own speed off. And especially if we're using Doppler shifts, because we're moving too, so we have to consider our velocity and the star's velocity to calculate how fast it's going. And generally, astronomers do this by using either the average of globular clusters, because they're all symmetric around the sky and orbiting around the center, so they should average out to zero velocity, or distant galaxies that essentially aren't moving at all relative to the center of the galaxy. And when you do that, you find that this is a rotation curve of the galaxy, and this is not actually what you expect from what we see in the light. You expect this to drop off much faster because there's less stars and gas as you get farther away from the center of the galaxy. But we don't see that. We see it stays relatively flat, meaning there's a lot of mass still happening out here where we don't see so much light. And this tells us that a large fraction of the mass that's affecting the motion of the stars through gravity is some kind of matter that we cannot see, detectable only by its gravitational effect. Astronomers call it dark matter, and it seems to make up most of the matter in the galaxy. So it's very mysterious. People have spent decades looking for it, and we'll discuss this in more detail next week. What's at the center of the galaxy? Well, things get exciting because there's a lot of energy near the center of the galaxy. There's light year long streams of material going here and there. But the very, very center, this is a view of the inner 2 light years of the galaxy, which is the direction of the constellation Sagittarius. There is so much interstellar dust between us and the center of the galaxy, we cannot see into it in visible light. I'm not sure what wavelength this image is, probably infrared. But you can detect radio waves, infrared, X-ray, gamma rays from the center of the galaxy. And what we know is that somewhere in this very, very small area, it's still well within this box, there's a very small object, maybe 10 astronomical units across. So the distance from the sun to Jupiter is emitting very, very intense radio waves. And we've named this object Sagittarius A star, or Sag A star. And we know now it is a supermassive black hole. Basically, we can detect where it is and exactly where it is by looking at the motion of stars in the center of the galaxy and mapping out their orbits over time. And this is in a very small region in the center of the galaxy. That's a 2,000 astronomical unit area. So a lot of stars in a relatively small area. And this is by tracking out all these orbits, you can pin down exactly where this object is and its mass roughly. And Andrea Getz, I talked about this a couple weeks ago. She's a professor at UCLA, got the Nobel Prize in Physics for this discovery in 2020, showing where this supermassive black hole was and what its mass was. It's over 4 million solar masses. So how did you get such a big black hole? When we talked about black holes a couple weeks ago, we said that they form when a massive star, say maybe 20, 30 times the mass of the sun, reaches the end of its life. Its core collapses and doesn't stop at a neutron star. It keeps collapsing until it becomes a black hole. It has so much gravity in such a small area that light can't even escape from it. But that's only, when that happens, it's maybe only 10 solar masses, not 4 million solar masses. So what we think must have happened is it must have started as that kind of black hole. That's how you make a black hole in the first place. But very early in the galaxy, when there was a lot of gas in the middle of the galaxy. And then over the 14 billion years of history of our galaxy, that black hole attracted a little more gas, grew a little more as gravity field got bigger, attracted more and more and more, and this happened over and over and over time until it built up to this very, very massive thing. So we think most galaxies have black holes with their center light, which we'll talk about next week. So that's what's at the center of the black hole, of the Milky Way. What about the actual formation? How did we get to this place? Why does the Milky Way exist? And I will say the galaxy formation, definitely galaxy form, is a major unsolved problem in astronomy and astrophysics. Many people publish many papers collecting new observations of all kinds of as many galaxies as they can, trying to understand how galaxies form and evolve. Most people agree that it's got to be related to some extent to a simple model we'll call the collapse model, that it's kind of like the formation of stars, but on a much larger scale. Instead of starting with a small, relatively speaking, cloud of gas and dust that collapses to form the sun, you start with a much, much larger cloud, million light year cloud with 100 billion solar masses of material, and it collapses under its own weight and breaks up into stars to make the galaxy. there's some evidence that this is at least a rough idea of what's going on from population 1 and population 2 stars. We'll talk about this in 3 steps, this model. In step 1, you have this large cloud, and it's not mostly, it's pure hydrogen and helium from the Big Bang. We'll talk about the Big Bang in a couple weeks. There's no heavier elements yet. And and it's also not shaped like a flat disk. It's a big spherical, spherical-ish cloud. And because there's random motions in it, it starts to condense, and some of the gas will collapse to form the very first stars. And these stars should have very low amounts of heavy elements. And the fact that we see these population 2 stars that have very little heavy elements, and that they're not in the disk, that they're in kind of in random locations in this sort of spherical area around the middle of the galaxy, support this idea that they're very early formed stars. And so they separated from the gas as they formed. And the very most massive ones would have exploded pretty early on and then built up more heavy elements into the galactic cloud. And the cloud itself is rotating and gradually collapsing into a disk shape, just like we think the molecular clouds that form the sun collapse into a disk shape. And by the time it's forming an actual disk, enough heavy elements have been built up from supernovae going off and making heavier elements and more heavy elements that we see the population 1 stars, and they're mostly in the disk. So the fact that we have this difference between population 2 stars and their compositions and population 1 stars gives support to this idea. So in the end, step 3, you have the population 2, what am I talking about? Population 2 stars in the halo. That's what we call this region around the disk, that are very, very low in heavy elements and very, very old. And the younger disk stars are population 1, are in the disk. So it's a general cartoon that works, but it doesn't explain all the details. But it really can work in a lot of ways. And this is just an example of somebody put up their own computer simulation to simulate this, where you start with a bunch of clumps of material, and they let them evolve with gravity, and you have to include some dark matter too, and you let everything interact with itself, with each other, and you let it, you give it a lot of time, and eventually you get something that looks like a spiral galaxy. There's a link if you want to go play with this code yourself. So it works, but it doesn't explain a lot of observations, so it's not complete theory yet. And there's a couple of important problems. Part of it is that the population 2 stars seem to have formed over a much longer time scale, but they were still forming population 2 stars after you start collapsing into the disk. And the simple model suggests that shouldn't happen. And you would expect the very first generation of population 2 stars themselves should have no heavy elements at all, because they would have formed from that beginning cloud that was just pure hydrogen and helium. And we'll come back to that in a second. And another thing that is observed, and you see these beautiful examples everywhere in the universe we look, galaxies are colliding into each other. There's a lot of galaxies, and sometimes it's spectacular like this, where you see 2 large spiral galaxies smashing into each other. Sometimes you have dwarf galaxies, small galaxies that are clearly being attracted and pulled into other galaxies. That's certainly going to affect how the stars evolve, how the galaxy evolves, and that's not taken into account in the simple collapse model. So modern models of the information are often computer simulations that include the possibility of mergers, and again, using observations to try and explain it. It seems to be, like this says, merging is starting to appear to be the rule, not the exception. That merging of smaller galaxy type objects with the bigger ones seems to be happening a lot. And we now have evidence for lots of very small galaxies having been absorbed into the Milky Way. So it's not as simple as just a simple big gas cloud that collapsed to form the Milky Way. More like lots of independent gas clouds that collapse to form their own little model of Milky Ways that combine to form what we have today. So I was talking about stars without any heavy elements at all. These are hypothetical. They're called population 3 stars. But again, the basic idea would be that the first stars in the galaxy had to be made of pure hydrogen. But we don't see these. And most stars are low mass and have lived very, very, very long lives. So small smaller than the mass of the sun or half the mass of the sun that formed at the very beginning of the galaxy should still be alive, and we should see it, but we don't see them. So there's three reasons we might not be seeing these population 3 stars. It could be that the very, very first generation of stars only made massive stars, that there was something different about the star formation at the very, very beginning of the universe. It only made massive stars that evolved very quickly and exploded as supernovae. It didn't make small stars that we would see today. That's possible. It could be that there are population 3 stars from that very, very first generation, but they were, what should we say, polluted or contaminated by supernova going off after they formed. So the second generation of stars that had a little bit of heavy elements could have evolved and formed and become supernovae, and some of that material been put back on the first generation stars if they were nearby. So we see these heavy elements, but they weren't there at the beginning. It's possible. Or it could be that they really are there, they're just very rare and hard to find, and that there's far fewer of them than the stars. I mean, the galaxy has been making stars over and over and over for billions and billions and billions of years. So the first generation might just be washed out in a sea of more recent stars. And this was the story that came out, a paper that came out just a week or two ago. This is news release from the University of Chicago, where they were announcing that scientists discovered the most chemically pristine star yet found in the universe. And this was, in fact, an undergraduate class from the University of Chicago, an astronomy majors class, got to go to Chile and use a telescope, and they discovered this star, which has this long, boring name. But what they found is it is almost pure hydrogen to helium. The heavier elements make up less than 0.00008% of the mass of the star. That's not zero. Population 3 this is still more than 0, so it's not population 3. This was probably among the very first population 2 stars, and it shows that we're continuing to find things with less enough heavy elements, and it's probably only a matter of time until we find the population 3 star. So what's going to happen at the end? Spoiler alert. The Milky Way will not last forever, because eventually all of the gas will find its way into stars. And then you'll have no more star formation. And basically, hundreds of billions of years from now, the Milky Way will fade, slowly spinning in space. A dark disk of stellar center. It's very poetic here. The point is the stars will burn out. They'll explode supernovae or planetary nebulae and white dwarfs and cool until nothing's left. Not every galaxy is the same as the Milky Way. And this is a teaser for the next chapter. There's a wide variety of different galaxies, and we're still discovering new things, especially in this era of the James Webb Space Telescope, which is allowing us to see further away than we have before, and thus back in time. And this was just a year ago, a widely reported paper from JWST that reported this galaxy is very red galaxy because it's so far away, so it's very redshifted. Because it's moving very fast away from us. We'll talk about that next week. And this galaxy, let's see, it made 10 billion solar masses in a very, very short period of time, 600 million years, and then shut down 700 million years after the universe began. So unlike the Milky Way, which made stars and made more stars into this just had an intense period of star formation and then just turned off. It's just been sitting there for ever since. So there's a lot of mysteries in the universe. And that is it. So thank you, and I will see you later. I can move that.